Okay, in this video, we are going to go over the this keyword and review pointers a little bit, and memory. Okay, so let's talk about the this keyword. Inside a class in C++, you'll often see this, the keyword this, floating around. And what it does is it is a pointer to the current object. So for example, let's say that we have this constructor here, and inside, this is some class that keeps track of bank account information. Let's say that the constructor passes in a name and a balance. And so the constructor needs to set the object's member variables, right? So you have these local parameters that are coming in through the function, but you have the same variable names used as your member variables, right? So oftentimes you use the this keyword to indicate that you're talking about this object's member variables, while these are just referring to these parameters that are passed in. So it's a pointer to the current object, and so anytime you need to access the current object's member variables, you can put this with the arrow in front of it, and that will make sure that you're accessing the one that you want to. You'll notice that it uses the arrow and not the dot because it's a pointer, and so the arrow dereferences the pointer, and the dot is actually just used to access a member's, like when you have access to an object, it accesses its member variables or member functions. So when you declare like an R vector object, like V, and then you do something like pushback, that's a period because V is the object itself, right? But when you're inside of the object and you need to access its member variables using this, you're going to use the arrow because this is a pointer to the object, so you need to actually go and follow the pointer to the object. So the arrow indicates that you need to do that. So let's look at some code and see if this can make a little bit more sense. So here we have this C++ code that we've looked at many times, where we have 3 R vectors declared and we're pushing some stuff back into it. When the compiler runs this, what it's actually doing is it is rewriting the code into C-like code, and this is originally what it was doing because C++ was built on top of C, and so at some point it's like rearranging all of these member variables and like member functions and rewriting them in a way that the compiler. So here it's basically saying, well, you're applying pushback to an object, so I'm actually just going to go ahead and put that object in by reference so you have access to it. Or the pointer to it, and that will give that function access to everything that it needs in order to do that functionality. So when you write pushback, this function here, you're accessing these member variables, right? So we talked about that in the previous videos, A and size. Well, what the compiler is actually doing is it's making sure that it has access to that object, right? So it's going to rewrite pushback and give access to a pointer to that object, and then it's actually referring directly to that pointer. And so this is a way for C++ to keep track of which object you're talking about, and the compiler takes care of a lot of it for you, so it's like optional in a lot of cases, but you'll see it a lot, so I wanted to make sure that you knew what this meant. So here's an example of the pushback function, and I showed you how to write it this way, and you don't see this in it at all, right? That's because A and size are scoped to this function in the class and they're not needed. Instead, you could write it this way. There would be no change in functionality if we included this into the code, and this way we're like making extra care what we're saying. We're talking about this object itself. It might not make sense right now because currently in all of the functions that we've talked about, Up until this point, we only have the active object in the functions. I haven't gone over any functions that have two different objects that you're dealing with, but we will. So in the last video of this week, we're going to talk about a copy constructor and an equal constructor. And in those, we're going to have multiple objects inside of the member function. And so we're going to need to be careful to keep track of which one we're talking about. The other really common use that you need a this operator is a constructor. So in this constructor, we have a local variable and we have a member variable that have the same name. So in order to keep track of which one you're talking about, here we're setting the object's member variables to the local parameters. And so you need to specify this so you can scope which variable you're talking about. Otherwise, as you can see with this code here, this is optional. You can use it or you can't. It's totally up to you which one you want to use. So now that we're thinking about pointers, and this is a pointer to an object, not the object itself, let's make sure that we remember how pointers work and how memory works in the computer. We're going to spend a lot more time on this next week and really start digging into memory. But for now, I just wanted to do a quick review. And maybe for some of you, you haven't seen this before. So your computer has like two different portions of memory. There's the stack and there's the heap. And the stack is basically where everything gets put that you don't, everything so far that you've written has been put on the stack. So anytime you declare a variable, like here we're declaring two integers, here we're declaring a C array, and here we're declaring a double. In those cases, those are all getting declared on the stack. The only things that get declared on the heap are things that you call new with, right? So everything when you write new next to it gets declared on the heap, which we'll talk about in the next video. So the way that memory is in your computer is that you have the stack and the heap, and it's drawn different ways by different people, and I like this way where the stack is growing from the top down and then the heap is growing from the bottom up, but you'll actually see it in both ways. The reason I like it drawn this way is because what you'll notice is with these hex numbers here, which are the memory addresses of these different locations on the stack, you'll see that the numbers are going down. Right, so just look at the last few numbers. The numbers are decreasing as you go down because the stack addresses grow going down. They get closer to 0. And then the heap is below it. And so if you've ever heard of stack overflow, it's basically when you put so much stuff on the stack that you reach the end of it, right? So there's a limit to how much can be stored on the stack. And so that's one of the reasons that you start allocating memory on the heap is if you have a lot of data, you can't put it on the stack because you'll run out of space. The other reason to allocate stuff on the heap rather than on the stack is when you need it later, right? Because the stack is going to destruct as you go in and out of functions. And so if you need access to it later, you're going to have to put it on the heap because the heap doesn't destruct. Again, we're going to talk about that a little bit later, a little bit more. But let's just do a simple example of how the memory in the computer works. So we are going to we're going to set up a variable x and store 42 in it. So what's happening here is that 42 is getting placed on the stack in a place in memory that can hold an integer. And so here is a memory address that fits an integer. And then here, when you declare this, it's going to find a spot on the stack that it can place y, and it's also an integer, so it's just going to go right there. Here, but it doesn't have a value yet, so it just knows that it's going to go there, but it, change this arrow a little bit. So it has memory allocated for that variable, but it doesn't have any value initialized yet. When you do a C array, the memory is sequential, right? So it places it in order that the C array is, and this is just a C array of 3 elements. So 91 is going to go here, 3 is going to go here, and 85 is going to go here. And then we have the double. The double is twice as big as the integer, so the double is going to take up more memory, and twice as much memory, so it's like indicated as twice as much with 2 full gray squares. And those memory addresses are per byte, so you'll see that there's 4, a difference of 4 between every memory address, and it's 4 times 8 bits to get, the proper amount of storage for each. Nothing we're really worrying about, but if you're interested in the details, that's how it works. So now here, we're just printing out a bunch of stuff, and you can actually just copy and paste this into an IDE, and you'll be able to see this yourself. It'll have different addresses, obviously, because computers have different memory addresses associated with their memory, but this is what you'll see. And when you print out the memory addresses of all that memory you allocated, you'll see what I'm pointing to here on the screen. So you'll see that the memory address of X is going to be the biggest memory address, and then you'll see that D has the smallest memory address because the stack grows down. Grows down to memory address 0. Let's see, what else? What's going to print out here? Well, it could be anything because we didn't initialize that memory. So whatever was in memory there, depending on the OS that you're using or the compiler that you're using, it could be anything. In many cases, it'll be 0 if you haven't run anything for a while. But if it's a big program that has lots of stuff going on, it could have any value at all there. What else was I going to show? So yeah, let me just write out what some of these things will print as. So if you print out X here, X is just going to print 42. If you print out its memory address, it's going to print out the memory address that it's pointing to. So in this case, it would print the hex address like that. But if you run this on your computer, it would print whatever memory address is there. What would print here? It could print anything. Maybe it prints 7 or something. It could print 0, whatever happened to be in memory there. That's why you have to initialize your variables, and we've seen a lot of problems with that so far, of people not doing that. And then again, this is going to print out the memory address of Y. So the memory address of Y is 28F62C. And then A. What is A? So A is a C array, and a C array, when you declare it, its variable points to the front of the array. So the front of the array, this is the C array right here, is actually the first element of the array. So if you just print out A, it's going to print 0, 28, F6, 28. And that's also going to be the memory address of the first element of A. So the square bracket operator goes to, it does the pointer arithmetic that's 0 away, so that's the first one, and then it dereferences it, so it actually gets its value. So A of 0 pulls out 91, but then if you put the ampersand sign, then it's going to find its memory address. So it turns out that these two are the same, 0x284628. These are going to be the same because one is pointing to the front and the other one is also pointing to the front. So I think that is pretty much it. So let me see if I missed anything that I wanted to talk about. I guess the only other thing is that C++ allows you to write beyond the array. So as you start writing with these C arrays in your data structures that you're going to be writing, if we did something like A of 500, or let's do something smaller, let's do A of 4, or no, let's just do A of 3, right? And we set it equal to something. It's just going to go and destroy this double that you just made. It's just going to replace whatever bits were there to store the double. It's just going to replace them with what you just did. So there's nothing inside of the C array that prohibits you from going past the end of the array. So even though you said that you only have 3, it doesn't care. And so as we start to move into writing these abstractions and using C arrays and pointers in order to store everything, like this is all under your control. So if you need to review memory and review pointers, you're going to need to do that because there's really no getting around it. Like you have to understand exactly what all this stuff is doing in order to make sure that you're designing these implementations correctly. So I already went over this in like first week video, going over like the operators, the star, the asterisk, the ampersand, etc. Just remember that the asterisk has lots of meanings. First, it's used to declare pointers. Then it's also used to dereference pointers. So here we have an integer x. We fill it with 42. We create a pointer to an integer, which we call p, which is just going to point to where x is. So let's say we have some memory here. So x is going to allocate memory on the stack, and then p is going to point to that memory on the stack. So if we print out p, it will give us a memory address. If we print out p star, it's going to give us the actual value that it's pointing to. We can also dereference p and update it with x times x. So this is going to be replaced with 42 times 42, which I don't know what that is. So 1764. So it will replace that value with 1764. We haven't changed x, so if we print out x, it will still be 42, etc. Now, another thing to remember, and this is something that you're going to see in the review of all these implementations, is that when you create a C array, the variable a is going to be a pointer to the front of the array. So when I create this a C array that I call a just points to the front of the C array. And so if I want to create a pointer to the front of that array, I can. So p is already an int pointer, and so when I assign p to a, it just points p to the front of a, or the front of the C array, which is also what a points to. So now when we do p of 1, right here, that's going to print out 6 because it's just going to go to the front of the array, do pointer arithmetic, and get 6 out. So that's some good stuff to review, is all this stuff with pointers and pointer arithmetic. So here's a couple other examples of pointer arithmetic that might be good to review if it's new to you. Understanding how to like move from memory using arrays and how the square bracket operator works. Again, really, really going to be important as you start moving into this implementation stage. Here's another thing I wanted to point out, which is when you start using pointers, one of the things that you're going to see is at the top of your class, when you create constructors and you create your member variables, you're often going to create pointers. So, you saw that with the rvector implementation, we created an a pointer, right? When you create it in the member variables, you're not going to initialize it, but it's not going to have an initial value. So if you try to dereference it, it's a pointer that doesn't point to anything, right? It's not like this doesn't have any memory that it's pointing to. It just is a pointer that can point to something, but it doesn't point to anything. So foo does not have anywhere where it points. Foo is just a dangling pointer, and you have all this memory, but it doesn't point to anything. Okay, so this is not what it's doing. So what happens is if you try to dereference it and put something there, so you're dereferencing this dangling pointer, it doesn't have anywhere to put the data, right? So the problem with that is that your code is going to be really confused because you're dereferencing something that doesn't have anywhere to go. So a good way to recognize that you have dereferenced something that hasn't been initialized to something is by making sure that all of your pointers have initial values. So for example, if you have a constructor that basically sets up an empty data structure, that means you won't have allocated any memory for it. What would be a good practice is to set that pointer to a null pointer, so that way if it's ever tried to be accessed, you'll get an error that can tell you what the problem is, right? Because it'll actually say that you're dereferencing a null pointer, which is what a segmentation fault is. Okay. So those are a few things about memory and pointers. I think one of the things to be aware of is as you start using pointers under the hood of your implementations and playing around with memory, is that I think this is a place where I see that a lot of students are in a lot of different places with their comfort level. So maybe all of this was like very much review and very much solid for you, and maybe some of this wasn't. And so it's really up to you to take the time you need to review pointers and memory so that you're ready to build these abstractions properly. It's one of the things when you program that you cannot just get away with like trial and error. If you don't know how your memory is laid out and you're not able to understand it, there's no amount of brute force plug and chug, like, try to every possible combination that will work. It will never work. So you have to be able to understand it. Okay, so that's it for this video.